Okay, imagine you're trying to measure the most violent, explosive collisions in the entire universe. But right in the middle of it, your measuring tape just suddenly breaks. What do you do? Well, astrophysicists just figured out an absolutely brilliant workaround. They've discovered how to use the gravitational ripples of colliding black holes to literally fix and tune their own broken measuring machines. It's a massive breaking discovery for astronomy, and we are going to break it all down in this explainer. So the dossier for today's explainer is a brand new research paper. It's titled GW240925 and GW250207, Astrophysical Calibration of Gravitational-wave Detectors. The lead author is A. G. Obick, and it was just published by the global LIGO, Virgo, and CAGRA collaborations. Now, I'm bringing this to you right away because this is honestly an incredible story. It completely rewrites how we can make sure our multi-billion-dollar cosmic observatories are actually working and giving us data we can actually trust. So, what exactly did they discover, and why should we care about this right now? Well, the researchers state the core of their breakthrough perfectly in the paper, saying, astrophysical signals can be used to infer detector calibration, essential to ensure the reliability of the Hanford data. To translate that into plain English, without this really ingenious mathematical fix they've just proven, we would have been completely blind as to where in the sky a recent set of black hole collisions actually happened. We had the raw data, sure, but without this new technique, it was basically just a useless blur. To really understand the massive problem they were up against, we kind of have to ask a weirdly simple question. How do you measure a ruler? Think about it. When your entire job is to measure the fabric of space and time, stretching and squeezing, how do you know your cosmic measuring tape is accurate in the first place? Guaranteeing that accuracy is, without a doubt, the hardest part of gravitational wave astrophysics. And let's just take a second to put the sheer absurdity of this scale into perspective. When gravitational waves from black holes actually pass through Earth, they stretch the 4-kilometer-long arms of the LIGO detectors by an unimaginably tiny amount. We're talking about detecting changes in distance that are smaller than 1/10,000th the width of a single proton. At that microscopic scale, literally anything, a truck driving down a highway miles away, a tiny drop in temperature, can completely throw the machine out of tune. Because these machines are that wildly sensitive, scientists have to use a really painstaking process called calibration. Basically, they mathematically convert the raw electrical outputs from the machine into true accurate measurements of spacetime. And normally they do this by literally pushing on the detector's mirrors with physical lasers, called photon calibrators. They constantly test the machine's response in real time. But what happens when that physical tuning system just completely fails? Well, that brings us right to the core mystery of this paper, which centers around the LIGO detector in Hanford, Washington. During two recent massive black hole collisions, things went totally sideways for this detector. First, during an event called GW240925, a procedural mistake gave the Hanford detector a massive 20% amplitude error. It was entirely out of tune. Then, during a second event, the detector was literally just warming up. The thermal lenses were still settling down, and those physical calibration lasers, they weren't recording anything at all. The Hanford data was effectively useless on its own. And you can see the real-world consequence of that broken calibration right here. If you look at the blurry, widely spread out colored rings on the map, that is your search area if you just accept the bad or missing calibration data. It's kind of like a detective trying to find a suspect who's hiding somewhere in the Pacific Ocean. But when the researchers apply their new astrophysical calibration fix, which you can see as those tight, precise rings in the inset box, it pinpoints the exact cosmic neighborhood. It takes a completely useless blur and turns it into a precise astronomical target. So, how on earth did they fix it without those physical lasers? Well, I like to call their solution the cosmic tuning fork method. Imagine you're about to play a concert, but your electronic guitar tuner completely breaks. What do? You listen to a perfect, familiar song on the radio, and you tune your guitar by ear to match it. That is exactly what these researchers did. Instead of relying on their broken electronic tuning lasers, they used the perfect, predictable song of the universe, the gravitational waves themselves, to tune the detector. Here's how this brilliant, improvised detective work actually played out. Step 1. They detected a remarkably loud, clear gravitational wave signal from these colliding black holes. Step 2, they compared that signal across the other functional detectors in their global network, specifically the Livingston detector in Louisiana and the Virgo detector in Italy, which were both perfectly tuned. Step 3, because the laws of physics dictate exactly what that black hole collision should look like, they reverse engineered the broken Hanford detector's error. They looked at what Hanford should have seen, compared it to the messy data it actually recorded, and mathematically forced the data back into tune. And the absolutely crucial point here is, it worked beautifully. The paper concludes by stating, agreement between results validates the GW-informed calibration, demonstrating the utility of an astrophysical signal. For that first event, they actually had a chance to double-check their math after the fact, and this improvised cosmic tuning matched their physical laser calibrations perfectly. So how confident should we be in this result? Highly confident. Now, the researchers are honest. They note it isn't quite as flawlessly precise as physical lasers under perfect conditions just yet, but it is an incredibly robust, proven backup system. So, what does this actually mean for the real world and the future of astronomy? Well, it ushers in a completely new era of resilience. We're currently building a global network of these detectors, and now we have a definitive failsafe. A single machine's calibration errors or offline lasers aren't going to cripple our view of the cosmos anymore. Plus, this extreme precision is an absolute requirement for what scientists call dark siren cosmology, which is using these black hole collisions to measure the actual expansion rate of the universe itself. Without perfect calibration, those mind-bending cosmic measurements are simply impossible.
This research just brilliantly illustrates that the universe provides its own diagnostic tools if we're just clever enough to listen to them. I mean, they literally use the cosmos to fix a machine built to measure the cosmos. Which leaves us with one final kind of wild thought. If the universe itself can calibrate our most complex, sensitive machines, what other cosmic mysteries are hiding right now in the noise, just waiting for us to tune into the right frequency?